Hi, and welcome to part 3 of this lecture. In this part, we're going to talk about state tables and state diagrams, and they're going to be tools that you can use in order to analyze the sequential logic circuits. So a state table is a multivariable table with the following 4 sections. It has a preset state, and that includes the values of the state variables for each of the possible states. It has inputs, and these are all the possible input combinations that are allowed, in the same way that we would have done for a truth table in the combinational logic lectures. Present state being at time t, whilst the next state is at time t plus 1, and also an output as a function of the present state, and also sometimes the input as well can be used in the function for the output. If we were to think of the state table in the same way as a truth table, then we have the inputs being these, preset state and input, and the outputs being the next state and the output. Here's an example state table, and it can be filled in using the next state and the output equations. These are given for the next state of A, that is, where A at t plus 1 is the next state of A, and B at t plus 1 is the next state of B. And notice that the next state of A actually depends upon the current state of A and the current state of B, as well as the input x at time t. B, on the other hand, depends upon A and also the input x. So despite this present state actually being a part of the sequential logic, for the sake of this state table, we see it like an input to the truth tables that we've worked on before. And so you should be fairly familiar with this idea of inputs, something happening, and then outputs on this side. The output function is y at time t. Notice this is y at time t, whilst these guys are the states at t plus 1, and the output, yt, depends upon the state of b at time t, the state of a at time t, and the state of x at time t. So I won't go through this line by line, but let's just do the first line. And we say for the first next state equation, we have a at time t plus 1 is a, which is 0, and x, which is 0, or b, which is 0, and xt, which is 0. So that equals 0. That's good. And then b at time t plus 1 is not a at time t, so that's 1 because this is 0, and x at time t, which is 0. So 1 and 0 equals to 0. For the output, we've got not x at time t, so that's 1 here, and either b at time t or a at time t, both of which are 0. So 1 and 0 or 0 is equal to 0. So this is the output there. Just do one more here, even though it's relatively straightforward. We've got a at time t is 1, x at this time is 0, or b is 1, and x, which is 0. So 1 and 0, or 1 and 0 is equal to 0, which is what we've got here. B is not a, so that's 0, and 0 equals 0. Not x at time t is 1, and either b or a. So we've got b being 1 and a being 1, so 1 and 101 is equal to 1. And that's the output that we see there. And you could fill in this state table for all of those possible combinations of the preset state and input to get the next state and the output. This is an alternate state table. Rather than showing the x at time t as its own column, we actually group it with the next state as well as grouping it with the outputs. Previously, we had columns of a, b, x, a at t plus 1, b at t plus 1, and y at t. This is a total of 6. 1, 2, 3, 4, 5, 6. Now we have 2, 3, 4, 5, 6, 7, 8 columns, which is more than before, but we have less rows. Here we only have 4 rows, where before we had the full 8 because we needed to express the possible values of x. So this would have been all zeros for x, and then there would have been all ones for x. This alternate state table is the way that we're going to be representing it because it matches well with our understanding of the K-map. These equations are exactly the same as the previous slide. See, this is exactly the same as the previous slide. And I'll just select this one here, where we've got a and b both being 1. To go through briefly, this is one that we didn't do before. And this will allow us to actually show both the values for x, both x at time t to equal to 0 and x at time t equaling to 1. Then we say, here we have x equaling to 0. So we say a is 1, x is 0, b is 1, x is 0 equals to 0. And that matches what we got here. Not a is 0, x is 0 equals 0. So that also matches what we got here. And y for x equaling 0 is here. We have not x, so that's 1, and either b or a, both of these are 1, so it gives 1. So that's good. And then doing for the other case, which is when x is equal to 1, 1, 1, 1, 1 equals 1, 0, 1 equals 0, 0, 1, or 1 equals to 0. So that matches what we got here. We get 1 for the a at time t plus 1, 0 for the b at time t plus 1, and the output y at t. Sequential circuits can also be represented in a graphical form called a state diagram. And a state diagram has two main types. One is more and one is merely, and we'll get to that in later slides. But state diagrams have the basic following components. They have a circle with the state name in it. We can call that either by numbers or by letters. So we can have state 1 and state 2. And then we have a directed arc. So directed meaning that there's an arrow attached to it only on one end, and that says that we can go between 1 and 2, which is from a present state to a next state for each of the possible state transitions, and maybe the next state transition is to go from state 2 back to state 1. Each of the arcs also has a label on it, and on that label we always have the input values. What was the input value that made this state transition happen? Perhaps we have x equaling to 1 meant that happened, and then when it's at 2, if x equals to 1 again, then it just stays at 2. If x equals to 0, then it goes from 2 back to 1, and at 1, if x equals to 0, then it just comes back to 1 again. I'll talk about the labels in the next slide because they differ for the two different main types of state diagrams that we're going to be looking at. So in terms of the label, let's just identify the state name is here state 0 and state 1. This type is called a more type, and notice how it has a slash here and then another value. This value here is the output. So it's in the form of state slash output inside a circle. So this is state 1 with slash output of 1. We still have these directed arcs and we still have what the input value was. So in this case, the input at time t was x equaling to 1, and that allowed a transition between state 0 and state 1. At state 0, when we had input value of x equaling to 0, we have this transition, if you like, but it's still transitioning back to the same state that it is at now. So it maintains the same state. Once we're in state 1, if we have an input value of x equaling to 0, then we return back to state 0. Whereas if we have an input value of x equaling to 1, then we stay in this state and we have an output of 1 whenever we're in this state. Now the difference is with this merely type here, we only have the state name inside the circle, and on the directed arc itself, we have both the input, x equaling 0, same terminology as we've had before, but we also have the output. So the big difference between the two state diagram types is the fact that this one has an output written on the arc, whilst this one has the output written inside the circle. We'll also show that it's sometimes possible to mix the two of them, and sometimes easier to understand a sequential logic circuit by describing it with one type or the other. You will need to know both types, so it's a good idea to practice them. Let's look at this state diagram. We have a bunch of states, we have a bunch of inputs, we have a bunch of outputs. Which type is this? So looking back to the previous slide, we see that merely has only the state written inside the circle. A more type has the state and the output. This one has only the state written inside. The state in this case is the values of A and B, the state AB, state AB, state AB, state AB, which means that it's obviously a merely type. The other key characteristic of a merely type is that on the arcs themselves, you don't just write the input, but you also write the output. So we have all of these outputs written on each of the arcs. So these state diagrams are actually a good way to explain quite simple and small circuits, even of the magnitude that you're going to be covering within this subject. But perhaps for more complicated circuits, it can be easier to use a state table. You need to be aware of both the state table and the state diagrams, but personally I like the graphical representation of the state diagram if you're trying to follow the operation of a circuit, whilst if you're trying to look something up, then it's usually easy to use the table. Two states are defined as equivalent if their responses for each possible input sequence is an identical output sequence. Alternatively, two states can be equivalent if the outputs for each input signal is identical and their next state for each input symbol are also the same. Here's an equivalent state example. Notice also that this is a mixed Moore and Mealy diagram. We have some of the states where there is a output included as well as the state. So this is of Moore type. And then some of the circles only have the state inside. In these cases, they have the output written onto the arcs. Let's focus quickly upon states S3 and S2. So these guys. Now let's think about the case where the input x equaling to 0 from both of these states occur. We have x equaling to 0 here, x equaling to 0 here, and when we're on this arc, we output 1 for both of these. And similarly, when we're in state 3 and we have x equaling 1, or when we're in state 2 and we have x equaling 1, then we have this output of 0, this output of 0. So that means that whether we're in state 3 or 2 and we have x equaling 0 or x equaling 1, then we have an equivalent output. So by this alternative definition, states 3 and states 2 are equivalent. And so we can replace state S3 and S2 by a single state, and this gives the state diagram like this. So where before we had state 0, state 1, 2 and 3, now we have state 0, state 1 and only a state S2. But if we look at this new diagram again, then we see that when we're in state 1 and we have x equaling to 0, or if we're in state 2 and we have x equaling to 0, then we have an output of 1 from either state. Or we're in state 1 and we have x equaling to 1, or in state 2 and we have x equaling to 1, then we have an output of 0 in either case. So therefore states 1 and state 2 are also equivalent. So we can replace state 1 and 2 by a single state, and then we have this new state diagram shown down the bottom with just state 0 and state 1. And this state diagram explains the state transitions just as well as the much more complex state diagram on the previous slide. So that's the end of part 3. In the next part, we're going to be talking in more detail about the Moore and Mealy state diagrams. So I'll see you then.